In this chapter, we're going to be talking about the transition between IPv4 and IPv6, specifically interoperation. The implementation of IPv6 is really long overdue, but it's barely present as a network technology on most of the internet, corporate and private networks. Unfortunately, that transition isn't as simple as installing some new networking hardware, adding appropriate software updates, and then flipping a switch. As IPv6 network infrastructure components are introduced, they will have to live in a mostly IPv4 world, but they also have to be able to communicate with other IPv6 devices over IPv4. As more and more IPv6 devices and networks are created, there's going to be a large and confusing mix of v4 and v6 traffic crossing each other's domains, allowing everyone who is connected to talk to each other using one or the other protocol version. So eventually the transition will be complete, and IPv6 will be the dominant version of IP around the world in due time. So until then, the interaction methods for v4 and v6 must be deployed and maintained. So in this chapter, we're going to talk about the various methods that allow IPv4 and v6 networks to interact, including dual stack and tunneling through the IPv4 cloud. We'll discuss hybrid v4 and v6 network and node types such as basic hybrid, nested hybrid, and true hybrid. We'll talk about how a v6 transition address works. We'll describe the various v4 and v6 transition mechanisms, so dual stack and IPv6 over IPv4 tunneling. We'll describe the different tunneling configuration types and their device interactions. We'll talk about ISATAP as a tunneling mechanism, its components, addressing, routing, and router configs. We'll talk about 6 to 4 tunneling, its components, addressing and routing, communication procedures, and its most recent status. And we'll talk about Teredo tunneling system, Teredo being named after a worm that would tunnel through the wood hulls of ships. Probably the most useful information today. Just kidding. Its components, addressing and routing, as well as its processes. So how can IPv4 and IPv6 interact? They're going to exist side by side indefinitely. Most of the internet, most networks are still v4 based, and the designers of IPv6 knew that this cutover would take a long time. There's going to be no moment when a switch is flipped from IPv4 to IPv6. The two have to find a way to coexist. And they created a set of techniques to allow v6 to function adequately in that v4 dominant world. There's built-in tools to allow v6 to support the legacy installations of v4 as the transition progresses. So a dual stack approach, implementations for individuals or small offices can be a good experiment, but they're limited by the availability of dual stack routers at ISPs and at the edge. So the most important dual stack machines are the routers themselves. So a dual stack router provides a connection between the v4 internet and an office that's switched to v6. So when we talk about tunneling through a v4 cloud, the internet will probably move to v6 from the edges in. So to translate, v6 will be adopted first by smaller organizations and then eventually by larger and larger and larger based on your tolerance for, I guess, pioneering. From the points of view of route aggregation and bandwidth usage, the smaller organizations are at the edges and high-capacity networks are at the center. So you have these islands of IPv6 in an ocean of IPv4. And how do they communicate through one another? Through tunnels. So an IPv6 packet is formed normally, and it's sent to a router capable of encapsulating it in an IPv4 packet. And the 6 to 4 tunneling method is an alternate scheme that's talked about in RFCs 3056 and 6343. So when we talk about rates of adoption, the biggest push for v6 adoption has been coming from those who weren't part of the initial, I guess, internet land rush in the 90s. The creators of certain technologies, especially mobile technologies, have two reasons to embrace v6. They want the address space. There's too many devices now, especially as IoT is supported by a lot of these mobile carriers. We're getting more devices than the address space provides, and the people using these devices want directly addressable addresses for their devices. So they don't want to have to go through a NAT or do some translation. They want to be able to directly address the device. And there's also improved communications in v6 that a lot of the carriers can benefit from. So there was industry reaction to transitioning to v6. So initially the service provider segment of the market pushed for the protocol because you could streamline the global routing table. It would eliminate private address spaces altogether, so that translation would go away. The router and switch vendors saw the protocol as a good marketing opportunity, so they could slap IPv6 support as a sticker on their boxes and put it in their marketing materials. And engineers saw it as a solution for some specific problems. So interoperability means one technology can work together with another technology. It's just a general term, and it's a concern for any technology because vendors sometimes develop technologies that are based on standards but don't work with each other, with the other vendors' technologies based on the same standards. And you have the same concern between IPv4 and IPv6. So you have successful communication at the IP layer that requires all devices to either run v4 or v6, where some kind of address translation might be needed to permit the two implementations to work together. So I mentioned NAT before, network address translation. It provides translations between the private IP scopes and the public IP scopes. And certain technologies such as VoIP and real-time audio-video don't work with NAT. So that's a problem. And when we transition to IPv6, there's a lot of benefits for certain technologies that need that directly addressable device to communicate with. So when you're transitioning, you have to consider all of the different devices and software systems around a network that need to be able to support the transition. Clients, servers, routers, gateways, VoIP networks, network management nodes, transition nodes, firewalls, IDSs. It's not just getting every switch to work. There is a whole host of software and hardware that needs to be able to communicate. And on the software side, again, you have network management utilities, infrastructure apps, system apps, end user apps, software-based firewalls, high availability software, security software. You have the hardware side and the software side. Everything needs to be able to support this transition seamlessly with a minimal amount of change. So on Windows, when we talk about transitioning to IPv6, Microsoft offers a large collection of learning materials, and it's available on TechNet. One of the TechNet pages, IPv6 support, and Microsoft products and services has a lot of products, and whether they offer full support, limited support, or only full support for IPv4. Microsoft provides support for v6 from Windows Server 2008 onward and Vista onward, and it supports ISATAP as well as direct access in all of those. IPv6 address availability and component support are other obstacles to deploying an IPv6 solution. So while most service providers are beginning to upgrade their infrastructures to support IPv6, the assignment and distribution of addresses has not been widely implemented. And really, this is just immaturity of the deployment and immaturity in the consumer market as well. So it's kind of almost a catch-22. Consumers will deploy IPv6 when they're forced to, but providers are unwilling to sink funds into supporting v6 if there's no market for it. Most v6 deployments are Asia and Europe. These are areas that were behind the deployment of the initial IPv4 infrastructures. And as we talked about, it's really a catch-22 problem where the demand only is going to happen based on both the consumers and the providers wanting to transition. So what's next? Convincing executive managers that deploying a v6 solution is it's a robust and a necessary strategy for their business, because the benefits such as return on investment, so ROI, or business enhancement, it's not visible. I mean, if you go to your CEO and you try to propose this technical transition to IPv6 for your company, you're going to be hard pressed to convince that CEO they should dump the funds into it, because honestly, right now, you're not going to see a lot of benefit from it. Your organization is hard pressed to find any benefit from moving from v4 to v6 from a return on investment perspective. Doesn't mean you can ignore it. It's like buying cybersecurity insurance, right? You're not going to see an ROI, but if you don't have it and then you get hit with ransomware, you're done. IPv4 and v6 have been DoD mandatory standards since 2005. So, for instance, if you're going to be interacting with the government, especially DoD, you're going to have to support both and follow their standards. So federal contractors, for instance, what's the ROI? Well, we'll get the contracts. So if you don't support both of these in your implementations, you're now excluded from business. So it's really about hedging against risk at this point, but direct ROI isn't truly present. So hybrid v4, v6 networks and node types. So as we talked about before, network admins won't be able to simply flip a switch and transition their networks from v4 to v6. There's going to be a transition period where both versions of IP coexist in the same environment. And as software and hardware components are upgraded, v6 devices will need to be able to talk to each other over a v4 infrastructure. v4 and v6 nodes will need to communicate with each other either over a v4 core network or over a v6 core network, over different subnets, some of which will be v4 and some v6. In general, these mixed environments are called hybrid networks. And here's an example of a basic hybrid. Network model. So the basic hybrid network model is an example of how IPv6 capable sites communicate with each other over the IPv4 internet backbone. So each site is presumed to contain IPv6 individual nodes, and each site possesses a gateway that manages v6 to v4 transition traffic. v6 nodes encapsulate their v6 packets in IPv4 data packets and then transmit them to the default local site gateway. The gateway forwards these packets from the v6 network through the v4 internet using tunneling technology, and at the receiving site, also presumed to use an IPv6 gateway and be IPv6 capable, the packets are received, removed from the IPv6 encapsulation, and routed to their destination. Here we see a nested hybrid network model. So the nested model can be considered an adaptation of the basic hybrid model. So the core v4 internet remains the same, but sites can be v4 or v6, and a nested combination of the two. And in the nested model, the most likely design would be that small IPv6 island existing within the ocean of a larger IPv4 network. And this is the true hybrid network model. So the true hybrid model can represent a number of hybrid configurations, but it assumes the site has a variety of different subnets based on IP version implementation. So this model assumes the backbone is v4. The site gateway needs to have the same dual stack abilities, so as each subnet gateway, because it will be managing both v4 and v6 traffic at the site. So one of the challenges in v4, v6 communications is the issue of addresses. So v4 addressing and v6 addressing are radically different in terms of format, size, and memory requirements. So we talked about a few weeks ago that v4 uses a 32-bit address space and v6 uses a 128-bit address space. v4 uses dot notation, so 192.168.0.1. And v6 uses a colon notation, so and hexadecimal, so FE80 double colon 2D57 single colon C4F8 single colon 8808 single colon 80D7. An IP address parser attempts to translate that v4 address into its v6 equivalent. And there's a few different transition address methods. So there's literal IPv6 addresses and URLs, and then there's stateless IP ICMP transition algorithms, so SITs. IPv4 and v6 transition mechanisms are technologies that are used to allow the protocols and network infrastructure elements to be used in the transition from one version of IP to the next. More specifically, they're methods and address types that provide for communication between network nodes that use only IPv4 or only v6 to interact with each other or with network resources. And that transition requires multiple stages. Dual protocol stacks for v4 and v6. So a dual stack protocol for a host or router is implemented at the level of the device's operating system. So it allows the device to support both v4 and v6 either as independent protocols or in a hybrid form. Most operating systems have IPv6 enabled by default. So Windows 7 and later, Mac OS 10, Mac OS 10, 10.4 and later, and current Linux distros. So until this point, we've been using the terms dual stack and dual layer interchangeably, but they're really different types of architecture. So in the dual IP layer architecture, a network node possessing a dual IP layer architecture has both IPv4 and v6 protocols operating in a single transport layer implementation. So here again is an example of a dual IP layer architecture. And again, this is a single transport layer accessing the various IP versions. In contrast, the dual stack architecture, in this there's a computer possessing a dual stack architecture maintaining separate stacks of both the network and the transport layers. So in other words, each version of the IP protocol, the network layer has its own upper layer protocol stack at the transport layer. So in this figure we have an example of a dual stack architecture. And in this we have an example of dual transport layers accessing IP versions. So neither dual IP layer nor dual stack architecture requires a v6 over v6 tunneling to be effective as a transition mechanism. Dual architecture nodes can produce either v4 or v6 packets and then forward them to a gateway. The dual architecture capable sending node, if sending to a v4 destination, can construct a v4 packet and send it to the gateway. The gateway transmits the v4 packet without any form of encapsulation across the v4 network infrastructure. Another implementation of the dual architecture works as a transition mechanism, but requires no tunneling at all. So the dual architecture capable node would need two network interfaces, one for v4 and one for v6. The v4 interface would use the default route for a v4 gateway for normal network communications across the v4 network architecture to v4 destinations. The v6 interface would send traffic only if its own subnet and the sending node could create and use the v6 packets. So essentially, you just have two network cards, two network interfaces, one for v4, one for v6, without any tunneling or translation. v6 over v4 tunneling is used to allow v6 network nodes to send packets over a v4 network infrastructure. So the situation requiring this tunneling mechanism is on a network where the network nodes are v4 only, v6 only, or dual enabled. Remember, v4 and v6 tunneling is a challenge, especially for v6 header construction. The v6 path MTU for the destination is configured at a value of 20 less than the path MTU of an IPv4 destination. Here's an example of IPv6 over IPv4 encapsulation. And here's a Wireshark view of protocol nesting for the v6 over v4 encapsulation. So in terms of DNS infrastructure, we know that DNS records and DNS name resolution management are handled differently in v4 and v6. DNS servers have to be configured for dual stack. So we talked about 4A records under IPv6. DNS servers have to support both A and 4A records to allow names to be resolved into addresses. But in mixed environments, the resolver libraries and network nodes, they also have to have the ability to support both A records as well as 4A records. So when we talk about mingling v4 and v6 and tunneling configs, the tunneling mechanism for configurations, they're defined by RFC 4213, and they're used to describe the various device connections requiring v4 to v6 tunneling. So the encapsulator is at the node at the sending end of the tunnel, and it's responsible for encapsulating the IPv6 packet in a v4 header and then transmitting the packet in the tunnel. The decapsulator is the receiving node at the other end of the tunnel, and it's responsible for reassembling any fragmented packets, removing the IPv4 header, and processing the v6 packet. So there's several device types upon which tunneling configurations can be applied: router to router, host to router, router to host, and host to host. When we talk about router to router paths are most likely to use configured tunneling because they require specifically configured endpoints to the tunnel. So configured tunneling requires that an administrator configure the endpoints of the tunnel. Otherwise, the configuration is performed automatically by the configuration mechanisms of the operating system. And here's an example of a router to router tunnel. In the host to router and router to host configuration, this tunneling topology represents the first and last legs of a packet's trip from a source to a destination. For host to router, v4, v6 nodes tunnel their v6 packets to an intermediary v4, v6 router, and that can be reached over a v4 infrastructure. This tunnel spans the first segment of the packet's end-to-end path, eventually leading to the destination node. So the router and to host tunnels are the last segment in the path and are created by the v4, v6 router that's the last hop of the v6 packet. And in this figure you see the host to router and router to host tunnels. So in host-to-host, we have two IPv6 nodes that are linked directly using a tunnel over a v4 network infrastructure, and the tunnel describes the entire end-to-end path rather than just one segment. So with both IPv6 nodes connected over the v4 network, the link between them represents a single hop. Each of the two nodes creates a tunnel interface for v6 over v4. The route usually indicates that both nodes are on the same v4 logical subnet. The tunnel is created using the sending interface, optional route data, and the destination address. And here we see again an example of a host-to-host tunnel. So in terms of types of tunnels, RFC 2893 originally specified the two different tunneling types, configured and automatic. But RFC 4213, which makes it obsolete, removed the references to automatic tunneling and the use of IPv4 compatible addresses. As we talked about earlier, configured tunnels require that endpoint addresses be determined by the encapsulator device from configuration data in each tunnel. So ISATAP, the intrasite automatic tunneling addressing protocol, this is used to connect dual stack IPv4 and IPv6 devices across v4 network infrastructures. So from the perspective of the ISATAP protocol, a v4 network appears as a v6 link layer. ISATAP enables automatic tunneling for both global and private v4 addresses and offers a non-broadcast multiple access NBMA abstraction, similar to what RFC 2491, 92, and 3056 discuss. So ISATAP interfaces use the same basic tunneling mechanisms originally specified in RFC 4213. So ISATAP automatic tunneling, and this can be applied to dual stack devices, implements router to host, host to router, and host to host address assignments. So any two IPv6 nodes can communicate with each other over an IPv4 network infrastructure. ISATAP is supported on Vista and higher, and 2003 server and higher in terms of Windows. Apparently my mouse is not working. There we go. Okay. So here's an example of various ISATAP components sitting on a network. So router discovery for ISATAP nodes. The ISATAP interfaces use the neighbor discovery mechanisms, and that's talked about in RFC 4861 to detect the presence of other nodes, determine their link layer addresses, and maintain their own reachability data regarding paths to active neighbors. So because of the lack of multicast support, automatic router discovery can't be used. This is the reason ISATAP hosts use PRLs, so potential router lists, to maintain current information about ISATAP routers. So ISATAP nodes send infrequent ICMPv6 router discovery messages out of their tunneling interfaces to determine if the routers on the PRL are currently in operation and reachable. So in terms of ISATAP and addressing and routing, because ISATAP nodes support both v4 and v6, they can be configured with both addresses either manually or dynamically. ISATAP addresses use the locally administered interface identifier, so that has the format :0:5 EFE :w.x.y.z. So there's an example. When computers running Windows 7 or higher or Server 2008 or higher are assigned both IPv4 and IPv6 addresses, they're automatically assigned an ISATAP address. Each device involved in communicating on or off an ISATAP network uses different routes to different traffic from source to destination nodes. So an ISATAP network node has the option of using two different route types. And here's an example of ISATAP prefix addressing. much better than the one I tried to read to you. As you can see, the v4 address is embedded at the end of the v6 address. So you do have that kind of dual addressing capability baked right in. So in terms of communications with ISATAP, an ISATAP node uses host-to-host tunneling to create a connection to another ISATAP node on the logical subnet. So in terms of organizing host-to-host and host-to-router communication, all ISATAP nodes can be considered on the same logical ISATAP subnet. So the process of an ISATAP host communicating with a v6 node on a v6 capable subnet involves two different connections: a host-to-router tunnel from an ISATAP node to an ISATAP router, and a connection between the ISATAP router and the v6 capable subnet. So in terms of configuring an ISATAP router, computers running Windows 7 and above can be configured as ISATAP routers. So let's see here. I think we have a slide. All right. So here's some. If you want to configure the ISATAP router on one of these machines, you can run ipconfig whack all. The net shell interface, IPv6 show interface. So net sh interface, IPv6 show interface command shows the ISATAP index, and you can substitute that. For netsh interface IPv6 set interface 11 advertise equal enabled. But again, that index number is found in the IDX column. And here's an example of the output of ipconfig whack all. And here is an example of calling set advertising on the ISATAP interface. All right, 6 to 4. 6 to 4 is another v4 v6 transition technology that allows IPv6 packets to be sent across v4 network infrastructures, including the v4 internet, without explicitly configuring v6 over v4 tunnels. So the current specification of 6 to 4 is documented in RFC 3056, and it defines a method for assigning an interim and unique v6 address prefix to any site that already possesses one or more globally unique v4 addresses, and you can specify an encapsulation method for sending v6 packets over v4 using the unique prefix address. 6 to 4 avoids the need to configure the distinct tunnels required by ISATAP through the use of special relay servers. So 6 to 4 may be applied to a specific network node or to a local network. 6 to 4 addressing on a v6 network employs auto configuration, so that uses the last 64 bits as the host address and the first 64 bits as the v6 prefix. 6 to 4 technology is not without problems. It has a large number of misconfigured nodes and poor network performance. So again, here's an example of 6 to 4 addressing on a IPv6 network. Again, it employs auto configuration and uses the last 64 bits as the host address and the first 64 bits as the IPv6 prefix. And when we talk about 6 to 4, there's 4 basic components: a 6 to 4 node, a router, a relay, and a node router, also called a host router. And here's an example of 6 to 4 network infrastructure and the various components. Okay, so when we talk about addressing and routing in 6 to 4, any 6 to 4 site must possess at least one valid globally unique 32-bit IPv4 address in order for 6 to 4 addressing to occur. The address has to be allocated to the site by a formal address registry, so like an ISP or another service provider, and it cannot be a private v4 address. So while the first 16 bits of the prefix are always 2002, 13 bits are permanently assigned by IANA as the top-level aggregator or TLA identifier. So that means a numeric value of hexadecimal 2 combined with the v6 format prefix 001. So when that's expressed by IPv6 address prefix, it's 2002:/16. So the format of a 6-to-4 address prefix matches the format of a normal IPv6 prefix, and it, like any other valid v6 prefix, can be used to generate automated address assignment and discovery. So if the IPv4 address is assigned to the site dynamically, the 6-to-4 prefix is going to be dynamic as well. It changes every time the v4 address assignment changes. And the 6-to-4 router will use an on-link route to forward traffic to and from nodes on the private subnet. So a separate on-link route is used by the router and its 6-to-4 tunneling interface to perform router-to-router tunneling and other 6-to-4 routers and 6-to-4 relays. And a 6-to-4 relay uses an on-link route on its tunneling interface to perform router-to-router communications with 6-to-4 routers and router-to-host communication with 6-to-4 node routers. So in 6-to-4 communications models in a 6-to-4 infrastructure are node-to-node router and node-to-node, and the communication between 6-to-4 nodes and IPv6 hosts must go from the sending node to the router, from the router to the relay, and from the relay to the receiving node. So here's an example. I mean, for instance, if I have a 6-to-4 node and I want to send, I'm in node 1, I want to send traffic to a 6-to-4 node router A. The first step in the process is for node 1 to resolve the node router A's address using a DNS query. Node 1 then performs a route determination and locates the closest matching route to the destination address, which in this case is the default route for the next hop address of the local interface on the 6-to-4 router. Node 1 constructs an IPv6 packet and sends it to the IPv6 interface using the default route to the 6-to-4 gateway router. So using ISATAP and 6-to-4 together, an ISATAP node may be able to communicate with other nodes within its logical subnet, but it's unable to connect to computers on other networks. So normally an ISATAP host could not receive advertisements from a 6-to-4 router, and without those advertisements could never create an address that would let it use the 6-to-4 router as a gateway off its subnet. However, the 6-to-4 router could also be manually configured as an ISATAP router for the ISATAP network containing the relevant ISATAP node. So an A record must be added to the site's DNS server that points the 6-to-4 router's ISATAP name and resolves to an IPv4 address. So once that's accomplished, the ISATAP node will be able to perform a name-to-address resolution on the 6-to-4 router's ISATAP name, receive a router advertisement in response to a router solicitation message, and configure its link local ISATAP address. So the ISATAP node then configures a default route to the 6-to-4 router in order to send traffic off the ISATAP subnet using the 6-to-4 router as its gateway. All right, so Teredo, or the worm, is another v4 to v6 transition technology that allows v6 connections between two v6 network nodes across a v4 network infrastructure. So what makes Teredo different from ISATAP and its 6-to-4 is that it's able to operate from behind home routers and broadband devices using NAT, the network address translation. So in order for Teredo traffic to be able to cross v4 NAT and make v6 connections, the Teredo service tunnels v6 packets over IPv4 UDP using Teredo servers and Teredo relays. Teredo servers are stateless and are responsible for managing only small amounts of traffic between Teredo client computers. Teredo relays perform IPv6 routing between the Teredo service and IPv6 capable networks. So Teredo relays can also interoperate with network nodes using other transition technologies such as 6 to 4. So the components of Teredo, 4 essential components: the client, the server, the relay, and the host-specific relay. And a Teredo address are made up of 5 components: the prefix, the server IPv4, flags, port, and the client IPv4 address. And like other v4, v6 transition mechanisms, Teredo uses online and default routes. I would say, though, however, Teredo clients, they use routes a little differently than other Teredo devices. So, other devices. A Teredo node uses a default route that sees an IPv6 destination as on-link and uses Teredo tunneling interfaces. So here's an example of a Teredo address structure. And here is an example of the Teredo components and network communications process. So in summary, during the transition from v4 to v6, there's going to be a lengthy period of time, which we're in right now, where both protocols exist side by side. And there's several different v4, v6 hybrid networks and nodes that can be used to facilitate that transition. Transition mechanisms can use a dual IP layer architecture or a dual stack architecture. And v4 over v6 tunneling involves different device configurations. ISATAP is an automatic tunneling mechanism that allows v6 ISATAP network nodes to communicate across a v4 network. 6 to 4 is an IPv4 to IPv6 transition technology characterized by its ability to allow v6 packets to be sent across v4 networks and the use of relay servers. And Teredo is another v4 to v6 transition technology characterized by its unique ability to operate behind routers and broadband devices with NAT